Rigorous branching tree method for area measurement of planar regions. Aaron Cattell. 2025. Abstract. We present a mathematically rigorous extension of the recursive branching method, previously used to approximate circle circumference, to approximate the Lebesgue area of a bounded planar region. Under geometric density and scaling assumptions on the branching tree, we prove that a weighted sum of squared branch lengths, restricted to branches whose endpoints lie inside the region, converges to the region's area. The proofs rely on multiscale covering and packing arguments analogous to box counting methods in geometric measure theory. Introduction. Let omega proper subset symbol R2 be a bounded planar region with finite Lebesgue measure area omega. We construct a self-similar branching tree of line segments starting at P0 set membership symbol omega, whose endpoints at each depth approximate omega at a sequence of shrinking scales. Given a geometric constant c greater than 0 and branch lengths Lk, we form the estimator n equals k equals 0 nkcl2k, where nk is the number of retained branches at depth k. We prove that an omega as n infinity. Branching model. 2.1 parameters. Fix L0, 0, initial branch length. Set membership symbol 0, 1 scaling ratio. M greater than or equal to 2, branching factor. 1. Alpha, 0, angular separation. N, recursion depth. Branch at level k has length. Lk equals L0k. Each branch at angle k produces m children with angles k plus j. Equals 1 m. Where the angular offsets j are chosen so that directions become dense in 0, 2 pi. 2.2 Retention condition. Branch at level k is retained if its endpoint lies in omega. Let bank be the set of retained level k branches, and nk equals bk. Area estimator. Define the estimator. N equals n. K equals 0. N. nkcl2k equals cl20. K equals 0. nk2k. The rationale: each branch endpoint represents a cell of diameter Lk, hence area L2k. Main theorem. We impose two geometric assumptions. 1. Angular density condition. There exists d greater than 0 such that for every angle interval I proper subset symbol 0, 2 pi, of length I, for sufficiently large k the branching process produces at least I d potential branches with directions in I. 2. Scale condition. 2 mk. M2, 1. Theorem 1, main theorem. Let omega be bounded and Jordan measurable. Assume angular density and M2, 1. Then there exists a geometric constant c greater than 0 such that lim. N infinity and equals omega. To prove this, we require covering and packing lemmas. 2. Covering and packing lemmas. Lemma 1, covering upper bound. There exist constants C1, C2, 0 such that for each k, the disks B, XB, C1 Lk. Set membership symbol BK. Cover omega up to a boundary layer whose area is at most C2 Lk. Thus, omega backslash B, XB, C1 Lk, less than or equal to C2 Lk. B set membership symbol BK. Proof. Because directions are dense, for every interior direction and sufficiently small scale Lk, a branch endpoint lies within distance O, Lk, of any interior point of omega. Points near the boundary may remain uncovered, but since omega is Jordan measurable, a boundary strip of width Lk has area O, Lk. Lemma 2, packing lower bound. There exists C3, 0 such that a maximal disjoint subcollection B, K proper subset symbol BK of disks V, XB, C3 Lk satisfies, in particular, pi C3 Lk 2 less than or equal to omega B set membership symbol BK NK greater than or equal to omega pi C3 Lk 2. Proof. Select a maximal family of endpoints with pairwise distance 2C3 Lk. The disks are disjoint and lie inside omega. Hence the sum of their areas is at most omega. Conversely, maximality ensures the packing radius C3 can be chosen uniformly. Proof of main theorem. 6.1 Choice of C. The covering lemma implies that one scale k contributes at least nk, C1 Lk, 2 almost equal to omega, up to O, Lk, error. To normalize this, choose equals 1, C2 1. Similarly, the packing lemma implies that the retained branches cannot overcount area if C is chosen appropriately. 3. 6.2 Lower bound on Liminfin. By lemma 1. Thus, letting k infinity, Lk 0, so nk greater than or equal to omega C2 Lk pi C1 Lk 2 and greater than or equal to CL2 0 nk2k equals L2 0 C2 1 omega C2 Lk L0k 2 2k equals omega C2 Lk liminf n infinity and greater than or equal to omega. 6.3 Upper bound on limsuppen. From packing, lemma 2, and the angular density assumption nk2k less than or equal to cm2 k. Thus, n equals cl2 0, k equals 0. Since m2 1, the infinite series converges, and less than or equal to cl2 0 c. Choosing c such that gives 6.4 Conclusion. We have CL2 0 lim sup omega less than or equal to liminf infinity nk2k less than or equal to CL2 0 k equals 0 m2 c m2 equals omega and less than or equal to omega n infinity and less than or equal to lim sup n infinity. So lim n infinity and equals omega. Algorithmic implementation. Given P0, L0, rho, m, alpha, and depth nmax. 1. Recursively generate branches to depth nmax. 2. Retain only those whose endpoints lie in omega C m2, k and less than or equal to omega. 4. 3. Compute nmax. Nmax equals 4. Increase nmax until stabilization. Extensions k equals 0 nkcl2k Higher branching, m greater than or equal to 2 yields scale condition m2, 1. Variable scaling, allow k with k1. J equals 0, 2 J summable. 3D version, replace L2K with L3K, scale condition M3, 1. Conclusion. With mild geometric assumptions, the recursive branching method produces a convergent area estimator. The result unifies boundary approximation, circumference, and interior approximation, area, within a single multiscale self-similar framework. 5.